differential equations and I have to solve them together. I can't just write the integral design equation or the difference design equation. Typically I have to solve them together. And we'll look at an example of that next class. Well, hopefully we'll get to it by next class. But in the meantime, in the time we have remaining, which is plenty of time, it's only 12 or 55, according to my watch. Yes? So let me finish the sentence. In the meantime, in the time remaining, we're going to talk about a very important topic called multiple steady states.
All right, so with these equations, obviously you can't solve together. Do you end up taking some like a Lagrangian approach to solve?
Why don't you wait until we do the problem? We're going to do a problem like that. Instead of talking in generalities, you'll see exactly how we do it. And if you have another way you want to suggest to do it, it makes more sense to discuss it in the context of a real problem. So, I'm talking generalities. To really see what I'm talking about, you have to. It's best to look at an example. Wait. And I promise you, we will do an example. Hopefully we'll get to it next class. If not, we'll start it next class and we'll do it the following class. But in the interim, I'd like to talk about something known as multiple steady states. Okay, what is the issue of multiple steady states? One of the first assumptions we made when we started deriving the design equations for steady-state flow reactors was exactly that word, steady state. When we derived the governing equations for the time rate of change of the concentration of the conversion in a CSTR and a plug flow reactor, we derived the unsteady balances, and then immediately we said steady state. Why did we say steady state? Because this is what kind of class? A steady state class? Hopefully you're not at steady state. Hopefully you're dynamic. This is an undergraduate class. Not just because this is an undergraduate class, but also if you're in industry and you're operating a reactor, your life is a lot easier if that reactor is operating in steady state. Nothing's changing. You can when you go to sleep at night, it's at a good 95% conversion. You come back to work the next morning, it's still at 95% conversion. That's a good thing. Now, if you remember, we solve the design equation for assuming steady state. And up until now, every time we solved the design equation, we got, let's say we were looking at a CSTR. In a CSTR, we had the design equation, tau was CA0x in out minus x in over minus RA out. And for a plug flow reactor, we have tau is CA0 integral dxa over minus RA, xa in, xa out. Hopefully I didn't leave out any factors. What we assume, well, and typically RA was a polynomial. We had polynomial kinetics. And it might be a polynomial with an exponential in the k, an exponential in t. But up until recently, when things were isothermal, then it was just a polynomial in k, in x, polynomial in the concentration in x. And we always tacitly assumed, because it always worked out that way, that when we solved this equation, so we got a polynomial in x out, that we would get only one solution that made any sense. So one solution that was real and positive, and it was x between 0 and 1. And the other solution, when we had the quadratic, was negative or imaginary or something goofy. And similarly, this is algebraic, we also assumed the same thing, and we always found the same thing to be true with plug flow reactors. There was only one solution that wasn't goofy. Well, who said that always has to be the case? Who said that there aren't some kinds of kinetics, or if you like, once I allow things to be non-isothermal, where I not only have polynomial, but I also have exponential from the Arrhenius. Once my rate constants are exponential in t, and t depends on xa, from here, t is linear in xa. So in this, let's say t is linear in xa. If t is linear in xa, then I've got an exponential in XA multiplied by some polynomial in XA. Who's to say that if I have an equation that's polynomial in XA with coefficients that are exponential in XA, that there's only going to be one solution that's not goofy? There's no law. So let's see if we can construct a situation and see if it happens, and if it does, what it means. So I'm going to take the simplest possible case, the absolute simplest possible case. And that case is, let's say, a first order irreversible reaction. That's got to be the easiest kinetics I can think of. But I'm going to allow this to be non-isothermal. But I'll allow it to be adiabatic. So I'm still making it. It's non-isothermal, but it's adiabatic. So what? But it's going to be exothermic. Yeah. Say a first order reaction, constant density. I'm trying to pick a problem that's really easy. So hopefully I can avoid any of these nasty issues. Avoid difficulties. This problem was originally analyzed by Lilienroth in, I think, 1907, a long time ago. And then it was forgotten, or no one noticed it, and it was analyzed again, essentially the same analysis got published again in like 50 years later. So sometimes you could do good work and no one notices it because you're ahead of your time. Anyway, okay, so let's see what happens in this case. What's the rate? RA. A goes to products. Minus RA is equal to what? What's minus RA?
Right. K times CA.
K CA. And K is K0 e to the minus E over RT times CA. Okay, so if you remember, we solved this. We found that CA over CA, and here I'm going to let, again, I want to keep things simple. I'll let the inlet equal to the reference state. So CA over CA0 is equal to 1 over 1 plus KT, tau, in a CSTR. I'm doing this in a CSTR. C over CA0 is 1 over 1 plus k tau, and this is equal to 1 minus XA, because for a constant density system, CA over CA0 is just 1 minus XA. CA is CA0, 1 minus XA. So I can solve for XA. It's equal to XA is equal to, well, 1 minus this. That's 1 plus k tau minus 1 is k tau over 1 plus k tau. So now let's plug in for the Arrhenius. This is equal to K0 e to the minus E over RT, CA. I'm sorry, I don't need a CA. Times tau over 1 plus K0 e to the minus E over RT times tau. So that's an expression for A from the design equation, which we said the design equation is nothing more than the mass balance. Is that clear, what I've done so far? But we also have another expression for XA from the enthalpy balance. Here it is. And here, Q is 0. Get it? There's no Q. So I just have this. So this is equal to, from the enthalpy balance, CP1, T2, T minus T0 over minus delta H, heat of reaction. And now I'm going to set these two equal to each other. Remember, steady state. This assumes steady state. All right, so let's set them equal to each other. So I have And just for fun, I'm going to multiply by delta H, minus delta H. So I've got Cp T minus T0 is equal to minus delta H R times K0 e to the minus E over RT tau divided by 1 plus K0 e to the minus E over RT tau. Now notice, instead of what I spoke about here, instead of making this T of XA times a polynomial of XA, I went the other way around. I left this as T, and I turned XA into a function of temperature. You go either way. And what I would like to do is I would like to plot this equation. But before I plot it, I would like to interpret it. So this, remember, is nothing more than XA. Cp T minus T0 is the heat required to raise the temperature of the reactant mixture. Notice I dropped the 1. I could leave the 1 here. But here I'm assuming, I'd make things simple, I've assumed Cp1 is about equal to Cp2. So this is the heat required to raise the temperature of the reactant from the inlet, the reference state, to the temperature of the reactor. And this is a CSTR, so there's only one temperature of the reactor, unambiguous. It's the temperature of the reactor. T0, T1, T, same temperature. And this is the amount of heat produced. This is XA, and this is minus delta HR, and this is the heat produced by the reaction. Heat needed to raise temperature of reaction mixture from T0 to T. I want you to notice something about the characters of these terms. This, notice there's, what's the word I've underlined? Someone read that word for me? Produce. That's a production term. And needed, I can, instead of needed, I could say consume. So this is a production term, this is a consumption term. Think of it that way. This is an interpretation. Okay, now what I'd like to do is I would like to plot the left side of the equation and the right side of the equation. And I'm going to plot it on curves. So this is x. I'm going to plot it as XA versus T. Or XA, remember, I'm going to plot it actually, that's for the interpretation. I'm going to plot it as the left-hand side or the right-hand side. So the mass balance and the heat balance. So if it doesn't really matter. What you could say is what I'm really plotting is XA times minus delta H. Both sides are equal to that because they're equal to each other. So if I plot the mass balance side is the right side. So let's plot the mass balance side. All right. So this is as a function of temperature. It's my independent variable. All right. So let's look at the case where the temperature is really, really low. When the temperature is really low, the exponential gets really tiny. If the exponential is tiny, then this, if it's tiny enough, this term is small compared with 1. So that tells me that, and this is really tiny. So it starts increasing. And it looks like it's increasing more or less exponentially, because the numerator is increasing exponentially. So it starts small, and it starts increasing exponentially. Then what happens? Eventually, it becomes big enough that it competes with 1. And eventually, because this is increasing exponentially, t gets big enough that 1 is negligible. When 1 is negligible, what's the limit of this equation? 1, it goes to 1. The numerator and the denominator become the same. So eventually it increased exponentially, and it has to turn over and flatten out. So that's what mass balance on the side has to look like. And I didn't mean to make this look like it went up, went down, ever. It's just going up. Okay? Let's now look at the other side, the blue side, the heat balance. The heat consumed, the heat balance. The heat consumed is Cp T minus T0. What kind of curve is this? Straight line. It starts at T0 and has a slope Cp1. Well, let's say T0 is over here. I've got 3 possibilities. Either the slope is really high, or the slope is really low, or I have an intermediate value where the slope looks like this. Let's look at those 3 cases. Remember, the height, this height here is a measure of XA. It's XA scaled by the heat of reaction. It's essentially XA. If you're working at ExxonMobil and you're trying to convert, from crude oil, you want to get gasoline, a good mixture of gasoline. Do you want a high XA or a low XA? Assuming you want to keep your job. You want a high XA. So if CP is really big, the heat, as soon as I produce a little heat, I suck it all up, and that keeps the temperature real cold then, and you get a really low XA. That's not a very good situation. On the other hand, if CP is really tiny, so a little bit of reaction, and it heats up a lot, well, that's good, because now the curves cross, and is equal when the curves cross. That's a high, that's almost 1, conversion 99%. You're ready to be shopping around for that new car, if you can get gas for it. On the other hand, if you're at some intermediate value of CP, look what happens. I've got 3 points where they cross. That is, there are 3 different temperatures and corresponding XAs. For each temperature, where is it? For each temperature, here we go. For each T2, there's an XA, corresponding XA. There are 3 different temperatures where the 2 curves cross, where I have equality. There's this one, and this one. Well, that's troubling. That is, if I'm at this steady state, then I'm getting 98% conversion. My boss is happy, and she's going to recommend me for a promotion. If I'm at this steady state, well, I don't know, it's might be enough to keep my job, probably not going to get a raise this year. And if I'm at this steady state, well, then I'm going to be looking for a new job. Okay, so the first question is, what happened? Well, what happened was that even for this simple situation, this is simple, first order irreversible constant density. How much simpler can you get? Adiabatic, I'm not doing any heating or cooling. I just have a heat of reaction. Most reactions have a heat of reaction. And it says I can get in trouble even there. Well, let's examine these 3 steady states. And let's see if there's anything we can do to get ourselves from the unemployment line to the money line. Well, let's see. So what we're going to do here is a poor man's or a poor woman's stability analysis. Usually stability analysis requires a little bit more math. But here we can do it. Let's see how we're doing on time. Okay. Yeah, so here we're going to do a poor person's stability analysis. Let's say we're sitting at this steady state. So we arrange for the system to be at this steady state. And what happens if it's the winter time and someone comes in to the plant and leaves the door open? And it's cold outside. So all of a sudden the plant gets a little cooler and the temperature of the reactor is affected by that and goes down 1/10 of a degree. Just a little bit, a tiny amount, 1/10 of a degree. Well, if it goes down 1/10 of a degree, then instead of being this temperature, it might be here. And notice the pink curve is higher than the blue curve. Well, the pink curve, we said, is the mass balance is this, pink. Blue. And that says that the heat produced when I move to the left slightly exceeds the heat consumed when I move to the left. So when I'm no longer at steady state, if I'm producing more than I'm consuming in heat, what's going to happen to the temperature? It's going to increase. So if I move to the left a little bit, that's okay. The system's stable. It's going to move back. What happens if, on the other hand, it's the summertime and someone leaves the door open and the plant is in the Caribbean? So you open the door and all of a sudden it gets warm. So that means I move a little to the right. But if I move to the right, the blue curve consumption is higher than production. So the net effect is I'm going to cool the reactor down, so it's also going to move back. So this is a stable, steady state. It's stable to small perturbations. Not 20 degrees, but a tenth of a degree. It's stable. Yes?
So, do you think of this in terms of the slopes of the mass balance or the heat balance?
I'm thinking of this as which curve is higher and which curve is lower. Now, if I go to this steady state, the same thing happens. When I move to the right, the blue curve is higher than the pink, just as here. When I go to the left, the pink curve is higher than the blue. So just as this was stable, this is also stable to small perturbations. That's why I use a small delta. Okay, but that brings us to this steady state. This steady state, look what happens. If I decrease the temperature by a tenth of a degree or a hundredth of a degree, and I move to the left, so I'm a little cooler than I should be, just a hundredth of a degree. Well, the blue curve, consumption, is higher than the production. So if consumption is higher than production, what's going to happen to the temperature of the reactor? Loud. It's going to go down. So even if I'm off by a hundredth of a degree, because consumption is higher than production, it's going to start getting colder and colder and colder. And where is it going to stop? At the unemployment line. On the other hand, if I were at this steady state and I heated it up a hundredth of a degree, well, the pink is higher than the blue. It's going to start getting hotter and hotter and hotter until I'm in the Cadillac showroom. But Romney has 2 Cadillacs. Okay, so this one is unstable. Small perturbations. So what does that mean? Real life has perturbations. Always. These perturbations, instead of a hundredth degree, can be a thousandth of a degree. How are you going to avoid a thousandth of a degree perturbation? You'll need a very active controller that adds heat or subtracts heat as necessary to keep this stable. But these guys without controllers are stable. So what happens in real life, unless you have a controller that's adding and subtracting heat as necessary, you'll never see the steady state. Because long before it gets steady, there'll be a perturbation that moves it this way or that way. But what we'll see is that some conditions end up migrating to this steady state. Some conditions migrate to that steady state. And what we can see from this curve is that this is the dividing line. If I start at a temperature above this value, I'll get here. If I start at a temperature below that, I'll go there. Since I want this one, that tells me that when I have multiple steady states, the way I start up the reactor determines which steady state will appear. And that's assuming that it will eventually become steady. That's also not always the case. But if the reactor is to become steady, for example here, then depending on whether I start the reactor down here at a temperature and corresponding concentration to the left of this, or to the right will either send me to the unemployment line or to the Mercedes showroom. And I want you, the take-home lesson of this is that even in the simplest possible case, adiabatic, first order, irreversible, constant density, I can get in trouble. So clearly any other situation has the potential to get me in trouble. Yes.
Okay, so the way you have this drawn, right, the unstable point looks like an inflection. Is that
Looks like an infection.
Inflection.
Inflection. Yes.
So is there any relation between the
That's just an accident, by the way, that it's inflection. Had I drawn the curve a little bit higher, it wouldn't have been at the inflection point. I drew that just good way because it kind of makes the three crosses as obvious as possible. But it didn't have to be. I could have made the slope slightly higher. Okay, so now what can I do? You know, this can keep you up at night. Because let's say there's a perturbation, let's say you're operating here, and there's a perturbation that's not just a half a degree, but big enough to get you just past here. And it'll run all the way down there. In order to cure it, I need a big perturbation to get me past here for it to run up here. It would be nice if I just had this situation. So to get this situation, well, notice what I would want to do is somehow I'd want to decrease CP1. How do I decrease CP1? One way. Decrease the inerts. When I increase the inerts, I get more CP1. I decrease it. So if I had inerts, if I took inerts out, then I might be able to get to this situation. Another way of doing that is increasing minus delta H. Because remember, delta H should have been in the denominator down here. So that would change the slope. Or if you like, increasing delta H raises the pink curve. So now, the thing is, I don't usually have control over delta H. That's the E reaction. But sometimes I do. Sometimes the delta H might be a function of certain thermodynamic variables that I can play with. But usually the control I have is to try to change the inerts. If I had inerts in there, I can take them out.
Maybe getting ahead of myself, but since this is the simplest case, and we see that we have three potential
Steady states.
steady states, are there cases, the general cases, more common cases, more complex than that, more than?
Yes, and then that's exactly the right question to ask. This is simple first order. There are situations where instead of 3 steady states, I have 5 or 7. There are other situations where I don't have any steady states that are stable. I may have one steady state and it's unstable. And there are no other steady states. So what happens in that case? I need something else to be stable. Well, there's a certain kind of situation. There's a model called the predator-prey model. Where what you get is you have a steady state that's unstable. I'm not telling you what I'm plotting. I'm plotting concentration of A versus concentration of B here. And this is an isothermal case, where there's one steady state that's unstable, and what happens is, instead, you find what's called the limit cycle. This becomes unstable, and what happens is you have a concentration that goes, each concentration goes up and down with time, and it just like cycles, and this is called the limit cycle. And the model for this, the simplest model, is if you look at an island with foxes and rabbits on it. So this might be the concentration of foxes, and this might be the concentration of rabbits. And if you have a situation where rabbits reproduce, that's what they like to do, foxes eat rabbits. And foxes can only reproduce when they're not hungry. So here you have foxes eat rabbits and reproduce, rabbits just reproduce, and foxes can die of old age. So you just put those three reactions in, and what you get is what's called a limit cycle solution. And what happens is, and what does this mean physically? The physical interpretation is, what happens is, you have, let's say you have lots of rabbits around. once you have lots of rabbits, you have a lot of rabbits, then what happens, and you have very few foxes. So what happens then is the foxes say, party time. They start chewing up the rabbits, so the amount of rabbits go down, and their population goes up. Because they have full bellies, so they're going out on the prowl. And they start making lots of little foxes. So you get lots of foxes, and all of a sudden there are not very many rabbits. Well, you don't have many rabbits, you got lots of foxes, they get hungry and they start dying, they start starving. So the concentration of foxes starts plummeting because they have nothing to eat. Well, then the few rabbits who are left say, coast is clear, they start reproducing again. And you go around in a limit cycle. I didn't draw the right shape of the limit cycle. It's not exactly a circle. But this is a case where there's only one steady state and it turns out to be unstable, and the limit cycle is the stable solution. So sometimes this can give you a big headache. You can have similar kinetics in a chemical situation. There are other situations. There's one called the Belousov-Zhabotinsky reaction. Where instead of getting a limit cycle or a steady state, the steady state is unstable. And what happens is you get what's called the chaotic solution. What does chaotic mean? Exactly what it sounds like. It means it works like the City College administration. Just kidding. What that means is the steady state becomes unstable, and the concentrations of the products just keep drifting. And they don't repeat. They go up, they go down, they stay within a band. They don't go to zero, they don't go to infinity, but they just keep changing with time, and they never settle down to a steady state or a limit cycle. And there were original models that showed chaos solutions in certain models of the weather. Some of the early models were weather models that showed chaotic solutions. And the Belousov-Zhabotinsky reaction was a reaction discovered in the 1950s. That's a reaction of maleic acid. Or maleic anhydride. And you can actually do that reaction, and you put a color dye in, pink and blue, and you watch to see, does it settle down to be blue? Does it settle to be pink? Does it oscillate? No, it just goes randomly from pink to blue to pink, and doesn't seem to have any regularity. And Belousov discovered this reaction initially in the early 1950s. And it's a famous reaction because he sent it for publication to a number of journals. And the response he got back was, stupid, this is impossible. And so the paper was never published. From a number of journals, he gave up. And then it was rediscovered about 10 years later by Zhabotinsky, who had enough evidence that he convinced people and he got it published. But it still is the Belousov-Zhabotinsky reaction, even though Belousov never got the results published, because Belousov was right and all of his colleagues were wrong. Any questions? Okay, well, I don't want to go on beyond the allotted time. So